So let's remind the steps again. We start with the superposition state with equal amplitudes, okay? We start with psi, an equal weighted superposition state, x. And then we invert the phase of the key value, x star, and then we do an inversion around the mean, which is just an inversion around the general superposition state psi. But the way we do an inversion is by the operator h u0 perp h. This simply changes the basis to all zeros if we apply the Hadamard transform, the Hadamard tensor n, of course. And then we apply u0 perp, which is an inversion around all zero states. And then we change the basis back to, this is actually Hadamard inverse, okay? But Hadamard inverse is equal to Hadamard, so it doesn't really matter if we wrote Hadamard inverse or Hadamards, they're equal to each other. So and then finally we change the basis back to the general superposition state psi. And so we get in the end, what we get is an inversion around the average of the amplitudes of the basis states. Okay, so then we have two separate crucial steps, the inversion of the key value, the phase inversion of the key value, and phase inversion of the key value. And we have inversion around the mean. But what happens if we apply them both? So let's start with the general superposition state, psi. Let me draw a graph. So we start with psi, and suppose that the y-axis denotes the amplitudes, alpha x. The x-axis denotes the basis states from 0 up to n minus 1. And all basis states are in equal superposition with the amplitude 1 over square root of n. So this is our initial state, where all the basis states are put into an equal superposition. So now the key value is maybe somewhere here. So this is x star, our key value, okay? The index that we want to find. Now if we apply the first step, the phase inversion of the key value, what happens now is apply step 1 and get something like, so all the states except the state of the amplitude of the key value will remain the same, except that the amplitude of the key value will be flipped. So this is x star, and the rest of the states are still they still have the amplitude 1 over square root n. Okay, but then what happens now is that the average, the mean value, is now dropped down just a little bit. Because the amplitude of the key value is flipped, we take the negative, so the average amplitude is dropped down a little bit. Okay, But then after the second step, when we do an inversion around the mean, now what happens here is, so right now the amplitude of the key value is -1 over square root of n at this stage. But when we apply the second step, when we do an inversion around the mean, what we get is a constant improvement on the amplitude of the key value. So now we apply step 2, inversion around the mean. Now, as I said, the average has dropped down a little bit here at this stage. So right now we do if we do an inversion around the mean, now the amplitude of the key value will go up to three over square root of n. Okay. And what about the rest of the amplitudes? Well, we started with 1 over square root of n, so this is the amplitude of the non-key values. So if we do an inversion around the mean, so this will actually, the amplitude will lower itself. The new amplitude will be below the average. So it will go even lower. This was the average. And the amplitude of the non-key values, they go below the average. So this is just one iteration. In the second iteration, we do the same. We do a phase inversion of the key value. So this will go to, the new amplitude of the key value will be -3 over square root of n. Okay. And then the rest of the amplitudes will remain the same. But then the average will go even lower. And then what we do is that, again, apply the second step, inversion around the mean. So the amplitudes of the non-key values will go even lower than the previous step, and the amplitude of the key value will go higher. So this is how we amplitude, that's how we control the amplitude of the desired state that we want to find. So we lower the amplitude of the non-key values, but we amplify the amplitude of the key value. So now we almost have the entire algorithm then. So Grover's algorithm, so this operation, the first and second step, the phase inversion of the key value and the inversion around the mean, this is called Grover's iteration. And this is simply the operation. So we apply the oracle in the first step, and then we apply h u 0 perp h. Okay, so this is Grover's iteration. If we write the entire algorithm, we can start with the state. So step 1 is to start with state all zeros. Okay, we have an n-dimensional vector. And then step 2 is that we apply the n-dimensional Hadamard transform. And then at step 3, well, first we apply the phase inversion operator, and then we apply the inversion around the mean. But here's a question: how many times should we apply the Grover's iteration? Well, this grows, the amplitude of the key value grows constant in a constant manner, right? First it was 1 over square root of n, and now here it's 3 over square root of n, and then the next stage it will be 5 over square root of n. So if we apply Grover's iteration, square root many times, then in the end, approximately, we will get to measure the key value with probability, with a high probability, let me say. So steps 3 then is to repeat Grover's iteration approximately square root times. That is, we first apply the phase inversion the oracle O, and then the next step of the iteration is to apply the inversion around the mean. Apply the inversion around the mean. And then we measure the qubits. If we want to draw the circuit diagram of the algorithm, then it would look something like follows. We start with all zeros. We apply the Hadamard transform. And then in the second input we have the qubit 1. We apply the Hadamard transform here. And then we apply the phase inversion of the key value, that is the oracle O. But then we apply the inversion around the mean, H, U 0 perp H. And then we measure the first register. So this part here is the Grover's iteration. So we do this approximately square root of n times. Okay, so there's a really nice geometric interpretation of Grover's algorithm. In fact, this Grover's iteration is just a rotation around in the two-dimensional vector space. If we imagine a two-dimensional vector space spanned by the key value x star and non-key values x, so this is, let's suppose, our key value x, and let's suppose that we have states orthogonal to the key value, and these are non-key values, x perp star. Okay, so the y-axis denotes our key value and x-axis denotes the non-key values. So this axis basically denotes the solution space, and the other axis denotes the non-solution space. So we have a two-dimensional vector space, and we start with the general superposition state psi, right, which is equal to 1 over square root of n summation x. And any general state, any general vector can be represented in this two-dimensional vector space in the trigonometric form, say phi of theta, can be written as cosine theta x perp star plus sine theta x star. So any vector lies in this vector space can be written in this trigonometric form. All right, so now the key value, actually, the vector x star, is obtained when this theta is equal to pi over 2, right? But let's go back to our initial state. We start with in state psi, okay? We start with the general superposition state with equal amplitudes. And then, so let's observe the effect of one Grover iteration on an arbitrary given state phi theta, okay? So we begin with phi theta, and we apply the first step of the Grover's iteration, which is phase inversion of the key value. And that is just actually applying a reflection around x star. Sorry, around x perp star. First step of iteration is a reflection around x perp star. Right, so that changes the sign of the key value. So what we get is, let me redraw this diagram. So we have psi here, we have phi theta, and let's suppose that the angle is theta here. Okay, so reflection around x perp star gives this vector. So this is the oracle O times phi theta state. And that is equal to cosine theta x perp star minus sine theta x star. So this is the new state after the first application of the Grover's, after the first step of the Grover's iteration. And in the second step of the iteration, we apply the average around the mean. And this is just a reflection around psi. Because inversion around the mean is just reflection around the general superposition state, psi. So now what we get now is this new state. All right, so this is h u perp h o phi theta. Now, as you can see, this is the result of a single application of Grover's iteration. And so our initial state was phi theta, we assumed. And then after the first iteration, we get closer to the key value. And the more we apply Grover's iteration, we get closer and closer to the key value. But we don't want to overcook, because otherwise if we do it more than square root n times, we overcook and then we pass the key value. So we need to be careful. We need to apply this exactly as square root n times. Okay. So this is the geometric interpretation of Grover's algorithm. And we assumed from the beginning that there is only one key value that we want to find. But for an n-item search problem, if we have m many key values, then we only need to apply the oracle square root n divided by m steps. So in any case, the speedup is quadratic. Now, in general, this doesn't give us the exact solution, right? It gives us a solution with high probability. And I'm saying that we don't usually apply this Grover's iteration exactly square root of n times, but we applied approximately square root n times. But in some cases, this algorithm gives us the exact solution. For example, and I encourage you to do this as an exercise, for case n equals 4, the algorithm gives the correct answer with probability 1 in exactly 2 steps.